All right, everybody. So I'm making some extra videos because I know we ran out of time last term, and I know we didn't quite get to cover the enthalpy calculations in the depth that I would have liked. So I'm going through the calculations so you guys can cover it over the holidays because we still need to do the mock next term. The last question is our enthalpy question. And I should actually call it enthalpy calculation because that's basically what you're trying to do in this question. I'm going to break this into multiple videos so that way you can learn each type of calculation, and it can be smaller bite-sized bits of information so you don't have to sit through and watch like an hour video. I personally think this enthalpy calculation is the easiest question out of the structure and bonding exam. But to be fair, I say that as someone who's good at math. This is actually a really nice question if you're good at math, because so long as you do the steps properly, you know how to do algebra, you write your units, you write 3 sig figs, it should be an easy excellence point. Now with the enthalpy calculation, it splits into 2 different categories, which is the bond calculation, and then there's also the, what I like to call the gram to mole to energy kind of style question, and you can also go in reverse too like that. So it's kind of like it's not a good way to kind of summarize all of it. It's just you're using that n equals little m over big M quite a bit, and you might occasionally use the concentration equation as well. So the good news is it'll be slightly familiar. So what I'm going to do is I'm going to split this up into the basically 5 different videos to explain each type of calculation. So the first one we're going to be looking at is the bond calculation. Now the bond calculation again works in 2 different ways. You could be asked, for example, you could be given all bond energies, and then from that you need to figure out the enthalpy, which is that delta H. Remember that enthalpy is just talking about the heat exchange in a reaction. If it is positive, it is endothermic, so the reaction absorbs heat energy, and if it's negative, it is exothermic and it's releasing heat energy. The other one that you can get from that is you get one that has one missing bond energy, but you're given delta H. So basically all this is supposed to work out as an algebraic equation. So looking at that first one, when I talk about bond energies, I'm talking about this information here. Basically, with every chemical bond that we have between 2 elements, there's a certain amount of energy that needs to be put in per 1 mole of that bond to break it apart. So remember, when we're trying to break apart bonds, we are going to need to input energy to like physically force them apart, like you're trying to take 2 magnets and pull them apart. And if you make that bond, however, you're going to be releasing that amount of energy. So I like to think about those magnets naturally wanting to snap together and make that kind of noise. So this is kind of all the information that we're thinking about, is all these different bonds and how much energy you can take to make or break those bonds. Obviously, it's the same. What you input to break it is going to be what's going to be output when you make it. And it depends on, you know, what 2 elements are bonded together and if it's a single or multiple bond. So the best way to kind of learn how to do this is by example. So I might try to do this and hopefully, oh dear, where did my camera go? Did you not like that? Hello. Now can we do that? And you're not going to get mad at me? Okay, I think that'll work. I might make this a little bit smaller and that a little bit bigger. The main thing I just want to show you is the question and the steps on how we do this. All right, and I'll just change this paper over. So in this first example, so I'm going to actually number it with this sheet so that way you guys are aware of what we're looking at. This is question style number 1. So I'm given all the bond energies and I need to calculate. So we have CH4 plus O2O becoming CO2 plus 2H2O. Now they do that and they also give you a whole list of the values. What you want to do as your first step is you want to write down all the bonds for the products and the reactants just so you know what you're working with. Sometimes they just give you the equation. Other times they're really nice and they help you visualize what the bonds look like. So I'm going to draw them out because I think it'll help us just count to see where everybody is. Be mindful of the coefficients in front because what that tells you is you have 2 oxygen molecules. It's a good chance to review how to do Lewis structures. You see how there's a 2 there. All right, so what I've done is I have listed out everything so I can see it. Now let's write down how many bonds I have for each one. Remember that this side here is my reactants. And this side here is my products. So this is what's going to be what I need to absorb to break all those bonds. And that's what I'm going to release. I should probably write absorb so you know what that means. All right, cool. So when I'm looking at these 2 things, I like to put a line down the middle so I know which one's which. When I go through and count, I have the carbon-hydrogen bond, and I have 1, 2, 3, 4. So I have 4 CH bonds. I have 1, 2 of the C double bond O. When I look at this side, I have 1, 2 of the C double bond O. Whoops, let me write 2 C double bond O. And then when I'm looking at the H2O, I have 1, 2, 3, 4 of the hydrogen-oxygen bonds. So I personally find it's really good to write out my molecules so that way I can visualize and see how many bonds are there and what bonds are present. So that's my first step. Then what I want to do is calculate how much energy is going to be required to break all those bonds. So I see I have a CH and I can look on my screen. They should give you all of the values you need. They're not going to give you the table that you guys saw before over here. They're just going to give you the ones that you need so that way it's less searching around. Anyway, I have carbon-hydrogen bonds, and I have 4 of them. So I'm going to multiply that by 414 to get what that is going to be contributing. So I'm just grabbing out my calculator. 414 times 4 equals 1656. With the oxygen double bonds, when I look at that, it's going to be 498. We have 2 of them, so 498 times 2, and that's 996. And then I'm just going to add those together. And that's going to be 2652. So that's how that one works out. Then I go and calculate the energy that's going to be released when these bonds are formed. So the the carbon-oxygen double bond is 804. So 804 times 2, which is 1608. And then the hydrogen-oxygen one is 463. And I multiply that together and I get 1852. And again, we add those 2 numbers together to figure out my energy released, which is 0.3460. So that's how I've done those first two, or those three steps. I want to say at this point, it is really important to show all your working, because the achieved requirement is that you have calculated either the energy absorbed or the energy released. So basically you have two chances to show the achieved. I find with this question, if you have the right answer, then great, tick, you get the excellence point. But if you make a mistake somewhere and you don't show your working, I automatically mark it as a not achieved because I don't know where the error is. If I see all the working and I can see where that error is, then I might be able to award some more points. So that's what we're looking at for that first bit. And then my last step is I need to take the energy that is required and subtract away the energy that's released. So that's really easy. It's just basically what you have set up in the direction of the equation. You just take that and subtract that away. So 2652 minus 3460 delta H, sorry, 6. Cool. And I get negative 808 kilojoules per mole. So some things to note, it's really stupid stuff. If you're getting all the way to this point, you might as well go for the excellence, because the only thing that's really kind of differentiating the merit from the excellence is, do you have your units? Do you have 3 significant figures? Do you have the right symbol, like positive or negative? So those are very minor things. It's a really, if you're doing all this work, just make sure you remember those little things, because otherwise, again, they'll mark you down to merit. It's a really strange way that they've awarded points there. The other thing I should point out is that you see how this is a negative number. That tells me that's an exothermic reaction. No surprise that that's releasing heat energy because we are combusting methane, and if we're burning methane, you would feel the heat coming off from that reaction. So that is your first example. This is a second example that I have. I will actually do that one as well, just so you guys can have 2 examples of the same style of calculation. But if you want, I would recommend that you pause this video here and you attempt to do this question, so that way you can check if you have done the process right. But if you're still really confused, you can just go straight into keep watching this. All right, let's move that back over there so we can see how this question works. All right, same steps that we're doing. So again, H2 plus Cl2, we have 2HCl. These are my reactants. These are my products. I find it's helpful just to kind of label things. Again, draw it out, because I'm a very visual person. You guys know I can't do visualization, so everything needs to be drawn out for me. The other benefit of drawing it out too is that a lot of people are thrown off because they see H2 and they think there must be 2 hydrogen bonds. There isn't. It just means that there's only 1 bond connecting these 2 hydrogen bonds. So that's, again, another reason why to kind of draw it out. Anyway, that's my list. When we're looking at that, there's only 1 HH bond. There's only 1 Cl-Cl bond. So that means that if we times it by the number for that, whoopsie, energy value, makes my life nice and easy. Don't have to do a whole lot of work there, because it's just times by 1. In this case here, we have 2 of the hydrogen-chlorine bonds, so we times that 2 by 4, 3, 1. I should also sum up that total. I'm just working a little bit fast because this is the second time you guys have seen it. 8, 6, 2. All right. So let's add these 2 numbers together. 4, 3, 6 plus 2, 4, 2. So that's 6, 7, 8, and then that's the only number on that side. So we do 6, 7, 8 minus 8, 6, 2. Delta H is going to then be equal to negative 1, 8, 4, kilojoules per mole. And that's it. All right, I'm gonna stop this video. We're gonna make the next one.